When we think of noise, we think of screaming, but that's not the kind of noise we're talking about. With the use of math and technology, we can create vast organic patterns, stunning game generations, and grand movie scenes using a mathematical technique known as Perlin noise.
Developed by Ken Perlin in 1983, this revolutionary technique generates stunning organic patterns that breathe life into digital world, from procedural landscapes to mesmerizing textures. Far beyond a simple tool for gaming developers, Perlin Noise bridges mathematics and art, transforming numbers into captivating visuals. Artists use Perlin Noise to create realistic clouds, waves, terrain, and even abstract, dreamlike compositions. By controlling parameters such as frequency and amplitude, they shape patterns that resemble even organic flesh. This technique allows for near infinite variations, making each artwork unique.
To create our Perlin noise image, first we start by creating a grid of squares. At the corner of each square, we create a vector called an influence vector with magnitude 1. Now we rotate each influence vector by a randomly generated angle. Let's zoom in on our first square. Each square is split into a number of pixels. For each pixel, there will be 4 corresponding distance vectors running from each corner to the pixel. Each distance vector has an associated influence vector, and for each of these influence vectors, we will take the dot product. The dot product is defined as the product of the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between both vectors. This dot product will give us a result between -1 and 1, which we can map to a gradient from black to white. Doing this for every pixel gives us a gradient. The next step in Perlin noise generation is called linear interpolation. Linear interpolation takes 2 points and a value between those points and returns the height of that value on the line between the 2 points. We can apply this to the color value and the x position of each gradient, giving us the following 2 gradients. Next, we do the same for the y values, giving us our final resulted gradient. If we apply this for every square in our grid, we get the following. As we can see, the space between each cell isn't perfectly smooth, and there are some kinks. To smooth this out, we will use our last step called the Perlin noise fade function. This was a function developed by Ken Perlin to smoothly transition between cells in Perlin noise. Applying this to each pixel in every cell will give us our final Perlin noise image.
Beyond static images, Perlin noise is a key player in animation and CGI. It generates flowing smoke, fire, and organic motion that looks natural. Many animated movies use Perlin noise to create dynamic textures that would be impossible to animate by hand. Many blockbuster films use Perlin noise to add realism to different fantastical scenes, such as creating massive armies as seen in The Lord of the Rings. In video games, Perlin noise does more than generate landscapes. It influences the entire artistic atmosphere. It's used to shape fog, waves, and even character animations, enhancing the artistic appeal of virtual worlds. Games like Minecraft rely on Perlin noise to create endless and unique terrains, offering players an ever evolving experience. This competition was made possible by the generosity of our donors and the support of the Department of Mathematics, School of Mathematical and Statistical Sciences, the Fields Institute for Research in Mathematical Sciences, and the Canadian Math Society.